Here in part 5, let's talk about carbonate formation and photosynthesis and how that results in a decrease in atmospheric carbon dioxide. One of the important things to recognize is that the carbon dioxide concentration of the atmosphere has been changing over time. At the time that the Earth formed about 4 billion years ago, we think that the atmospheric pressure was at least double what it is and maybe up to 8 times the pressure that we have today. The CO2 concentration would have been about 980,000 parts per million. We think that the Earth was largely carbon dioxide and methane as gases. There was no oxygen. But over time, over the first billion years, there was a huge reduction in the amount of carbon dioxide. That reduction of carbon dioxide, it turns out, was driven by geological processes, not by biological processes. The big decrease in atmospheric carbon dioxide, where both biology and geology come into play, wasn't until about 1.5 billion years ago. And coincident with that decrease in atmospheric CO2 was now an increase in oxygen. So let's talk about the processes that will decrease the amount of atmospheric CO2. We have silicate weathering, which is a geological process. Carbon dioxide in the atmosphere interacts with rock. The result is that calcium carbonate is formed and silicon dioxide. Of course, we know silicon dioxide as sand. So we have this geological process, and then we have 2 biological processes that will take CO2 out of the air. The first is anaerobic, without oxygen, CO2 fixation via photosynthesis, such as carbon dioxide combining with hydrogen sulfide and an energy source to result in a carbohydrate formation and sulfur reduction. Then we have aerobic CO2 fixation or photosynthesis, in which CO2 combines with water and energy, in this case from the sun, to form a carbohydrate and oxygen. So the only one of these 3 reactions that produces oxygen is going to be aerobic CO2 fixation. So we didn't have this pathway predominant until we begin to see O2 as a significant part of the atmosphere. Now we also have processes that increase the amount of atmospheric CO2. One is relatively small, but it's respiration, aerobic respiration, in which we take a carbohydrate plus oxygen to form CO2 and releasing water and energy. And then the second one would be volcanic activity. And we do know that there were times in the Earth's history when the CO2 concentration went up because of tremendous volcanism around the world. So we have processes that increase and decrease the amount of atmospheric CO2. Our planet, though, is a Goldilocks planet. It's a Goldilocks planet in which we have water on the surface, and if we have too much heat, that water vaporizes and we have no water left to support life. If there's too little carbon dioxide, then we have ice formation. So we can have an environment in which we have too much abundance in greenhouse gases, the Earth is too hot. And then we can have too few greenhouse gases and the Earth freezes. We have 3 primary greenhouse gases: carbon dioxide, methane is a greenhouse gas, and water is a greenhouse gas. The amount of water, though, and its influence is somewhat limited because it's driven by temperature. So the dynamic ones to consider are methane and carbon dioxide, and it's primarily carbon dioxide that has driven the changes between a planet which is too hot and a planet which is freezing. So we will come back to it in the future, but there are times in the history of Earth that the CO2 levels became so low that the whole world was covered in ice. We do know that about 2.3 billion years ago, 2,300 million years ago. The Earth entered its first snowball Earth situation, and for tens of millions of years, Earth was not blue, it was white, because it was entirely covered by ice. We'll talk about snowball Earth in class 11. Your draw to learn today is to begin to do a graph of how, over time, oxygen and CO2 have changed. I want to have a graph which looks at time over the last CO2 concentration over the last 540 million years, and then one over simply the last 780,000 years. Our estimates of O2 and CO2 here are based on mass balance calculations looking at the chemical composition of rocks. Over the last 800,000 years, we actually have bubbles within ice, and they come from a place in Antarctica called Vostok. And so we can drill down and get that ice concentration over the last 800,000 years. Since 1958, we've had observations from actual observatories, and we've seen the CO2 concentration increase from 280 to today 400 parts per million.